Welcome back. In this video, we'll be solving the problem from multi-cylinder inline engine, balancing of multi-cylinder engines. Before seeing this problem, we'll be revisiting the things we have discussed. If you are having a single slider crank mechanism with a crank radius r and reciprocating as m, if it is at an instantaneous angle of theta, then it will be having an unbalanced force mr omega square cos theta plus mr omega square cos 2 theta by n. This will be calling as primary unbalanced force, and this will be calling as secondary unbalanced force. The effect of primary unbalance can be taken in this way. Same reciprocating mass will be kept at a radius of r at the end, and this unbalanced force can be produced by this arrangement. So this is the primary unbalanced force produced by this arrangement. And similarly, the secondary unbalanced force is mr omega square cos 2 theta by n, which I can rewrite as m into r by n into omega square into cos 2 theta. Otherwise, I can write it as m into r by n into 2 omega the whole square into cos 2 theta. So in primary unbalanced force, you are having cos in theta terms, and here it is 2 theta. So the effect of secondary unbalanced force, I will be taking this expression while solving problems. This can be taken in a way: the same mass m is placed at a distance of r by n, and that crank is rotating at a velocity of omega, and the value, the angular position will be 2 times the theta. So this is the equivalent primary state, and this is the equivalent secondary arrangement. This we will be considering for solving problems. So here you are having a multi-cylinder inline here we will be considering the problem of a multi-cylinder, means 4-cylinder inline engine will be considering. Each crank and connecting rod of a 4-cylinder inline engine are given 200 mm and 800 mm respectively. The outer cranks are set at 120 degree to each other and has a reciprocating mass of 200 kg. The spacing between adjacent planes of crank are given to 400 mm, 600 mm and 500 mm. If the engine is in complete primary balance, determine the reciprocating masses of the inner cranks and their angular positions, and also find the secondary unbalanced force if the engine speed is also given. So based on this, first we will be drawing the diagram. This is a inline 4-cylinder engine, means all the cylinders, 4 cylinders are coming in the same side of the engine. So it is inline 4-cylinder engine. Here it is mentioned that the outer cranks are placed or spaced 120 degree with respect to each other. So outer cranks are one of this is the outer crank, and this is the another crank, and 2 inner cranks will be coming, whose angular positions we are not knowing. Here each of the outer reciprocating masses are given, which is 200 kg. First I will be naming the planes. Here 4 planes are there which are corresponding to the 4 cylinders. This plane will be named as A, this plane will be C, and this is D. A and D are the outer crank, and B and C are the inner crank. So at A, the mass of reciprocating parts, I will be naming it as MA is 200 kg, and similarly MD, this is MD, which is also 200 kg. And so this will be rotating, this crank will be rotating at some angular velocity omega. Then primary as well as secondary, this primary as well as secondary unbalanced force will be produced along the each line of stroke of all these 4 cylinders, and it is said that the complete engine, that means the 4-cylinder engine is in complete primary balance. Primary balance means the primary forces are balanced. Primary forces are balanced means primary force polygon is closed, as well as primary couple polygon is also closed. But we have mentioned in the last video that you cannot do complete balancing, means you cannot keep both the primary as well as secondary forces and couples balanced. Here there will be, here primary force and couples are balanced, but there will be some secondary forces as well as couple. In this problem, you have to calculate the masses which are coming in this cylinders, means you have to find the reciprocating mass MB, reciprocating mass MC, and their angular positions you have to find, and also you have to find the secondary unbalanced force. Here at all the planes ABCD, reference axis will be taken as this horizontal line. So this will be the reference axis, and each angular positions will be measured with respect to reference axis. Here it is said that A and B cranks are spaced 120 degree apart. So here I will be fixing the position of A crank at a plane A along the horizontal, then crank at D will be spaced 120 degree, and you are not knowing the angular position of the crank at B. Theta B is unknown and theta C is unknown, and at all planes A, B, C, D, the crank length is, that means RA, RB, RC and RD is 200 mm or 0.2 meter, and the spacing between the cylinders are also given. This spacing is 400 mm or 0.4 meter. This is 0.6 meter and this is 0.5 meter. So you will be using this spacing for solving the problem also. So this is the complete arrangement of the this multi-cylinder inline engine, 4-cylinder engine, and here we have mentioned that for balancing primary as well as secondary, first it is mentioned that it is in complete primary balance. So complete primary balance of each cylinder will be considered by placing the reciprocating mass at the crank pin. Means if you are having a reciprocating mass of MA, this will be placed at this crank corresponding to theta equal to 0, and if you are having a reciprocating mass of MD, then we will be placing that same reciprocating mass at this crank pin with distance RD from the axis of rotation at theta D, and you have to find theta B, theta C, MB, MC if the entire engine system is in primary balance. Complete primary balance means primary force as well as primary couple is in balance. So you will be considering first primary, means primary force and primary couples will be considered, then you have to calculate the secondary unbalanced force you have to calculate. So for considering the considering the primary balancing, you will be drawing the configuration of this crank. The planes A, B, C, D are given. The reciprocating mass will be shifted towards MA to produce the same unbalanced primary force, which is MA 200 kg at distance RA. All radius are 0.2 meter. MB not known, RB same, theta B how to find. So 4 unknowns are MB, MC, theta C and theta B, and at this end MD at 120 degrees kept at a distance of 0.2 meter. So this is in complete primary balance. So for this system, if you are considering the primary forces only, that is mr omega square cos theta general term, then their force as well as coupled polygon will be closed. So for considering the primary balancing, you will be making this table where first we will be filling the plane. 4 planes are there, A, B, C and D, and 4 masses are there. Mass A is known, which is 200 kg, MB you have to find, MC you have to find, and MD is 200 kg. Radius, each radius is 0.2 meter. So all radius are 0.2 meter, and force you will be multiplying, it is M into R term only you will be considering for constructing the force polygon. So it is 200 into 0.2, 40. This is 0.2 into MB. This is 0.2 into MC, and this is again 40. Next we will be taking distance from reference plane. So the question is, which plane will be taken as the reference plane? Here 2 unknowns you have to solve for, which is coming in plane B and C. So one of these planes will be kept as the reference plane. So here reference plane will be taken as the plane B, where the mass MB is coming. So so this is the reference plane. Next you have to measure the distances from reference plane onto the other plane. Since B is taken as the reference plane, distance from reference plane for this row will be 0, and A is coming on one side, the masses C and D are coming on the other side. So we will be taking distances with signs. All the directions in this direction will be taken as positive, and from B to C it is 0.6 meter distance, which is positive as it is coming in this direction, and from this reference plane B to D is 0.6 plus 0.5, which is 1.1 meter, which is also positive. but here this distance with respect to A will be minus 0.4 as it is in the another side. So we will be filling, this is minus 0.4, 0.6 and this is 1.1. Next you have to take the, this is actually primary couple. Primary couple about the reference plane will be taken, which is product of force into L, where you will be neglecting the omega square term. So mr into L, which will be minus 40 into minus 0.4, minus 16. This will be 0. This will be 0.12 into mc. This will be 44. And last column will be angle from the reference axis. In all planes, this is the reference axis. The horizontal line is reference axis and all the angular positions of this cranks are measured. This is 0 degree, this is unknown theta b, this is theta c and this angle is 120 degree. So with the help of this column, we will be constructing the primary force polygon. This should be a closed one, and this couple, this is the primary couple. With respect to this one, we will be constructing primary couple polygon, and this should also be closed one, since it is mentioned in question that it is in complete primary balance. Here the question is which polygon we will be drawing first. If you are considering force polygon, two unknowns will be there, 0.2 MB and 0.2 MC. If you are considering primary couple polygon, there is only one unknown which can be solved easily. So first we will be drawing the couple polygon, for which a scale is to be selected. Scale will be, you will be taking 16 is coming and 44 is coming. So you will be taking the 10 units in couple will be taken as 1 centimeter in the diagram. So this diagram will be having some reference line. First you will be drawing some reference line and a point will be marked. From this point we will be starting drawing the first vector. First vector is minus 16 and it is at 0 degree. So I will be making a point. It is at 0 degree line, but it is minus 16, means I will be coming in the negative direction. So I will be taking minus 16. So this point, first vector I will be getting. This is the first vector. So at this point I have reached. Next vector is 0 in this force polygon. So I know I don't need to draw this one. Next one is 0.12 MC at theta c. These values are unknown. Next we will be drawing the non-vector, which is 44 at 120 degree. So from this point I will be taking 120 degree. 120 degree means this will be coming somewhere around here, and this will be taken to a length of 44. Since this vector is couple is 44 centimeter, so 4.4. So this will be the end of the next vector. So this will be representing, this is the starting point, this is representing minus 16 and this is representing 44. 0 vector we don't need to draw this one, and the remaining vector will be closing this side, as it is mentioned that it is in complete primary balance, means the moment polygon will be closed one. So you will be joining this vector and this will be the final vector, and this will be representing actually 0.12 MC. You can measure this one, and also you can measure the angle. This angle will be measured with respect to this horizontal line, and the angle measured in this direction, from this is representing reference axis. From this direction will be giving you the theta c value, and this 0.12 MC if you are measuring the length of the vector and converting into scale, this is coming around 5.4 centimeter, means this is coming around 54 units. So if you are solving this one, you will be getting MC, and if you are measuring this one, you will be getting theta c. So here you will be getting the MC as 450 kg and theta c will be measured, and you can be obtain it as 315 degree. So this value MC is actually 450 now, and this angle is 315 degree. Now you can find 0.2 and MC will be getting around 90. This one is solved now. So next you have to find the value of MB and theta B. which can be constructed with the help of the this primary force polygon. So next we will be drawing the force polygon. While constructing the force polygon, you have 4 vectors, 40.2 MB, 90 that we obtained now, and 40, and each of these vectors angular positions are also given. So first we will be drawing the 40 unit vector. Before this we will be defining the scale. 20 units from this column will be taken as 1 centimeter. So first point for beginning the polygon will be marked. 40 will be drawn to a length of 2 centimeters and along the 0 degree, so along the horizontal line 2 centimeter will be drawn. So this is the end of the first vector. So this is representing 40. Next we will be drawing the second vector. Second vector is 0.2 MB unknown, theta b. So we will be going for the next 90 at 315. 315 with respect to the reference axis or horizontal, which is measured in this direction, 315. Otherwise 360 minus 315, which is 45. 45 will be coming here, and length of that vector is 90 in total. So to a scale it will be of 4.5 units length. So that vector will be coming somewhat of this length. So this is representing the 90 unit vector. Next I will be drawing a horizontal line at the end of this one for the constructing the next vector. Next vector is 40 unit vector at 120 degree. So from this point I will be marking 120 degree from the horizontal reference axis, so which will be coming along this direction, and that length of the vector is around 40 units in total. So to a scale of 2 centimeter. So that also I will be marking. That will be coming to a vector of somewhat this much length. So now the remaining side will be closed by this 0.2 MB for the polygon to in balance, couple to be in balance. So we have started here. We will be connecting these 2 points. So this vector will be representing, at the end of this vector we will be drawing the horizontal line representing the reference axis. So this was our first vector representing 40, second vector 90, third vector representing the 40 unit vector again, and this final closing side will be representing the 0.2 times MB vector. And the orientation with respect to reference axis you can measure, and this will be giving theta b value. If you are measuring 0.2 MB from this diagram, this will be coming to a scale of 4.4 centimeter. If you are converting 20 units representing 1 centimeter, then 4.4 centimeter will be representing 88 units. That means 88 is equal to 0.2 MB. From this you can solve for MB, and measuring this orientation you can obtain the value of theta b. If you are solving, you will be getting the MB value as 440 kg and theta b value will be equal to 162 degree. So according to first complete primary balancing, you have solved for all unknowns. So MB is 440 and this theta b is 162 degree. The first part of our problem is over. 4 unknowns are solved. Next we will be finding the remaining thing is you have to determine the reciprocating masses of inner crank. Inner crank il varuna mass MA, MB, MC, theta B, theta C obtained, and you have to find the secondary unbalanced force. That we will see now. We know that secondary unbalanced force is mr omega square into cos 2 theta by n, and already we have explained that this unbalanced force will be considered by placing a mass at a distance of r divided by n. This is actually r by n, where crank is rotating at omega square and the angle will be taken as theta, where primary unbalanced force is mr omega square cos theta only. So for primary if you are taking theta, then for secondary you have to take 2 theta. So based on this, the previous diagram we have represented the orientation for primary balancing. There this diagram we will be calling it as, actually this will be known as primary cranks. And now for considering the secondary forces, you will be redrawing with respect to the angle theta, and that diagram will be known as secondary cranks. So you are having theta A is 0 degree, theta B is, you have solved it, is 162 degree, theta C is 315 degree, and theta D is 120 degree. And now we will be drawing secondary cranks at 2 theta. So here theta will be, theta A for secondary crank will be 2 into 0, which is again 0 degree, and theta B will be equal to 2 into 162 degree, which is around 324 you will be getting, and theta C is equal to 2 into 315, which is around 630. 630 you can write it as 360 full rotation plus another 270 degree, and theta D is equal to 2 into 120 degree, which is equal to 240 degree. So with respect to this, you will be marking theta is 0, that is along the horizontal line. Next is 324. So from the reference axis you will be marking this one, and theta C is 270 degree. So this will be 270 degree and 240 degree, which is this angle. So this is actually for the secondary cranks. This diagram will be known as secondary cranks. And here you are asked to find the magnitude of secondary force. So secondary force will be each line of action or each line of stroke, secondary force will be this one. So along this for this cylinder or for this first cylinder, this will be MA into omega square by n. Similarly for all, this will be having secondary forces, and there polygon we will be drawing, and the resultant force we can obtain from that polygon. So here for the first cylinder, secondary unbalanced force will be MA into omega square by n at this 2 theta, that is 0 degree. For this one, MBRB omega square by n at 324 degree, and similarly this values we can obtain. MA is 40, that you can obtain from this table, 40 into omega square by n. MBRB is 0.2 into that solved value of final, 88 you will be getting. MCRC will be 0.2 into MC, that is 90 omega square by n. MDRD is 40 omega square by n. So these are the secondary unbalanced force for all the cylinders, and their respective orientations are also known. So with respect to this, you will be constructing the secondary unbalanced forces. If those polygon is a closed one, then secondary forces are also completely balanced. If it is not closed, then the remaining side, length of remaining unclosed side will be giving you the secondary unbalanced force. So you will be drawing, while drawing all terms are having omega square by n, so you will be drawing only this 40, 88, 90, 40 length vector will be drawn. And here while drawing a length of this 20 units for drawing, this is actually we are drawing the secondary force vector you are drawing, secondary force polygon you are drawing, and while drawing a scale of 20 units will be taken as 1 centimeter. So you will be drawing the horizontal line, first point will be taken here, and the first vector is 40 unit vector, which will be drawn at 0 degree. This angle is 0 degree, so along a vector of 2 centimeter will be marking, and so this is the end of the first vector, and from this vector next will be drawn at 324 degree at 88 or 4.4 centimeter. So from here 324 degree or 36 degree from this side, and that length of the vector should be around 44. So this will be drawn to 44, and again we will be drawing the horizontal line for marking the angle, which is representing the reference axis. So this is the end of the second vector. Next you have to mark, this is 40, this is representing 88. Next you have to mark the 90 unit vector, and that angle is this 270 degree. So you will be drawing 270 degree, means it will be coming vertically down, and length of the vector is 90 units or half, that means 4.5 centimeter. So this will be coming somewhere here. So this is the end of this vector, which is representing 90, and at that end also will be drawing the horizontal line. Next you have to draw the last force which is 40 units at 240 degree. So from this point I will be marking 240 degree. 240 degree means 180 plus 60. 180 plus 60 means it will be coming here, and that length of the vector is 40 or 2 centimeters. So I will be drawing. So this is the secondary force polygon. Since it is open, vector is starting here and ending here, since it is not closed one, there is secondary unbalanced force, and that unbalanced secondary force will be given by this vector. So this is the final thing which is asked in this question. So if you are measuring, this will be giving you the secondary unbalanced force. Here in secondary unbalanced force, you are only taking the M into R product. So if you are measuring, you will be getting a scale of, this will be measured a scale of 9.8 centimeter. If you are converting into this scale, 1 centimeter is representing 20 units. This will be around 196. So 196 is actually the product of M into R. So for getting the secondary unbalanced force, you have to multiply this M into R into omega square by N. So this is equal to 196 into omega square is, omega value is actually given in the question, omega value is 210 rpm, that you can convert. So it is 2 pi into 210 rpm divided by 60, the whole square divided by N. N is L by R. L is 800 mm or 0.8 meter, and R is 0.2 meter for all the cranks. So if you are solving, finally you will be getting the secondary unbalanced forces around 23,712 Newton you will be getting, and this orientation of secondary unbalanced force you can obtain from this direction. Means in this multi-cylinder engine you cannot completely balance the primary as well as secondary forces and couples. Primary force and couple is completely balanced, or primary balancing is complete, but here there is a secondary unbalanced force of 23,712 Newton. Secondary unbalanced couple about which it is not asked in the question. So we have solved this problem completely. Thank you.